Okay, so in this class, I would like to finish up the chapter on the band structures. We still have to develop the band diagram for the example of the barium titanate. And we will now use the results for the crystal orbitals that we obtained in the last class in order to determine this band structure. So in the last class, we first looked at the interactions between the 5s tin orbitals and the 2p orbitals of the oxygen. And so we said that at the point at lambda, the crystal orbitals are non-bonding. That is also at the point chi, the crystal orbitals are somewhat bonding, and at the point m, the crystal orbitals are, well, bonding for those that have, well, majority oxygen to p character, and completely anti-bonding for those that have primarily a tin character. So to be precise, I should also say that here at the point chi, for the crystal orbitals that have 2p character, the situation is slightly bonding, okay, while here, for this one, the situation is slightly anti-bonding. Okay, so that's now enough information in order to construct the respective bands. So I now go forward to the band diagram, and you see here the band which has primarily oxygen character, and you see that here you have the band which has primarily tin character. Okay, so we said at point lambda we have a non-bonding situation. Okay, so that means that this crystal orbital here has essentially the energy of an oxygen 2p orbital. Yeah. And as we go now from lambda to chi, well, we will go to a more bonding situation. So here at chi, we are somewhat bonding, but that's not the most bonding situation that we can have. As we go from chi to the point m, we will go to an even more bonding situation. Now at point m, the crystal orbital, we have the crystal orbital which is most bonding. As we go back from m to lambda, well, we will go back to the energy of a simple 2p oxygen orbital. Okay, so now, is there a question? No question? So now we also need to consider the band that has primarily 5s tin character. So the 5s orbital of tin has a somewhat higher energy than the oxygen 2p orbital. Okay, and you see that here at the point lambda, our non-bonding orbital, crystal orbital, has a higher energy than the other non-bonding crystal orbital, which we discussed previously. Okay, so now for the crystal orbitals associated with primarily tin character, we go from this non-bonding situation here to the somewhat anti-bonding in the situation at the point chi, and from that somewhat anti-bonding interaction at point chi to the most possible anti-bonding interaction at point m. And from point m on, we will go back, okay, all the way to the point lambda, where our crystal orbital has the same energy as the, well, 5s atomic orbital of tin. All right, so now we are done with these interactions. We can next look at the interactions px tin with px of oxygen. Okay, let us go back and see what the character of the crystal orbitals was at the different points, lambda, chi, and m. So here you see that we have a bonding situation at lambda, and an interbonding situation for the crystal orbital which has a tin character. Yeah. So here now at point chi, we have a non-bonding situation for both crystal orbitals, whereby this non-bonding crystal orbital has 2p oxygen character, while this crystal orbital has 5p tin character. So as we go from chi to m, we see that we remain here at a non-bonding situation, okay? And the same is true for the crystal orbital that has tin 5p character. So we go from bonding to non-bonding, and then we stay at non-bonding as we go from lambda to chi to m. Okay, so what does that mean for our band? Well, let us first look at the crystal orbitals that have primarily oxygen character. So these are the ones that have lower energies. So now initially we start out with the bonding crystal orbital here. Okay. And as we go from lambda to chi, we are going from bonding to a non-bonding situation. Okay. Now these non-bonding crystal orbitals have now essentially the same energy as oxygen to p atomic orbitals. Okay, therefore the oxygen, the energy value of this crystal orbital is the same as the energy value of this crystal orbital here. So now as we go from chi to m, well, we remain non-bonding. Okay, so in this region, therefore, our band remains entirely flat. And as we go from m back to lambda, well, we go back from non-bonding to bonding. So for the band that has primarily tin px character, we first have a completely interbonding situation. So we start out at high energy, okay, but then we are going back, going down here in energy to a non-bonding crystal orbital, and that non-bonding crystal orbital would have basically the same energy as a tin 5px orbital would have. Okay, as we go from chi to m, well, our band remains flat. Okay, because of our only non-bonding crystal orbitals to consider. And then as we go from m back to lambda, well, our energy increases again because we are going from a non-bonding situation to a completely interbonding situation. All right, so what is left to do? Well, we have also the py interactions to consider. So for the band that has primarily oxygen to p character, we determined that, well, at point lambda, we have a bonding molecular orbital. Okay. Now, as we go from lambda to chi, we see that we have still a bonding molecular orbital, right? And as we go from chi to m, we go from non-bonding to from bonding to non-bonding. Okay. So now for the tin band, we have here at lambda the most interbonding situation. The situation remains interbonding as we go from lambda to chi. And as we go from chi to m, we will go from an interbonding situation to a non-bonding situation. So now what does that mean for our band? You see that here. So for the, we can start again for the oxygen band. So at lambda, we have a bonding orbital, a bonding crystal orbital. Then as we go from lambda here to chi, the situation remains bonding and the band is flat. As we go from chi to m, we go along this way, okay, until we have a non-bonding molecular orbital at point m. And as we go from point m to lambda, we will go back to a bonding crystal orbital. Okay, so now what about the band which has primarily tin character? So we start out with the completely interbonding situation here. And that interbonding situation doesn't change as we go from lambda to chi. Then our energy decreases because we are going from a interbonding to a bonding situation. Sorry, from the interbonding to a non-bonding situation. And as we go back from m to lambda, we will go back to our completely interbonding situation. Okay, now we are almost done. We should still consider that both of our tin orbitals as well as our oxygen orbitals have pz orbitals. Okay, so these pz orbitals, they stand, or they are oriented perpendicular to the square plane that we consider. Okay, so that means that sigma orbital overlap between two oxygen atoms that actually stand above and below the plane. Okay, remember here that the tin is coordinated octahedrally. Okay, can be combined in the most bonding fashion. Yeah. But it can also be combined in an interbonding fashion. Okay. So that's at point lambda. So now how will that band develop as we go from lambda to chi to m to lambda? So now, because the orbitals are actually having z orientation, okay, they basically there's basically no orbital overlap in x and y direction. Okay, therefore, as we go from lambda to chi to m and back to lambda, the energies do not change at all, and that means that our bands remain completely flat. Okay, so these are these two red lines. This one here for the bonding of possible orbital overlap, and this one here for the interbonding situation. Okay. Last but not least, we should consider that we have not used all the available px and the py orbitals of oxygen. Okay, that becomes clearer when we actually go back here, for instance. So for instance, we have only considered px orbitals here of these oxygen atoms. But of course, there would be also oxygen atoms here and here and here and here and here that have px orbitals, but they cannot interact with the px orbitals of the tin. Okay, just because they don't produce orbital overlap. But of course, they are there. Okay, they remain non-bonding because there is no orbital overlap with the tin orbitals possible. Okay, so therefore they just remain non-bonding. Okay, and we can draw them as such, as a flat band into the band diagram. Okay, so now we just need to be also clear where our band gap is, and we can determine this by by counting the number of electrons in the tin atoms and in the 2p orbitals of oxygen respectively. So in an oxygen atom, we have overall 4 p orbitals, and in a tin atom, we have, the s orbitals being completely occupied, and the p orbitals being occupied with 2 electrons. So that gives 5 electrons, 4 valence electrons for the tin. Okay, so that means that our Fermi level is actually here. Okay, so all these bands here are being full. This one representing the 5s to p interactions. This one here, which represents the px-px interaction, having primarily oxygen character. This one here, which represents the py interactions, but also this one, which remains completely flat, but we need to fill it just because it has the lowest energy, resulting from the pz interactions. Okay, so this band here, these two, and that band here for the interbonding pz interactions remains empty. Okay, so that means that our Fermi level must actually be between well, here is the 2p non-bonding orbitals, and here the 5s O2p sigma star band. Yeah. So yes, question. I'm sorry, but I cannot hear you. Not sure why. Okay, can you type? The bands look like mirror images of each other for bonding and interbonding. Is that always true? I believe, good question. This may be often the case, indeed, but I would be careful to say if that's always the case. I don't see a compelling reason at the top of my mind why that should be always the case. It really depends on the orbitals that you're working with. So in the case of these orbitals, yes, but I would be cautious to argue that this would be always the case. I don't see actually a compelling reason why that should be the case, especially when here we have a very high symmetry structure, and especially when you actually lower the symmetry of the crystal structure, this may not be always the case. So I can look deeper into the question in order to answer it with certainty, but based on that, is there a reason why the blue and red band seem shifted up in energy in the valence band? Shifted up in energy in the valence band. Yeah, so you're saying, well, for instance, this one here has a certain energy value below the Fermi level, whereas this one here has a greater energy above the Fermi level. I think you can understand this using the analogy to molecular orbital theory. So when you have two orbitals and combine them to form a bonding in an interbonding molecular orbital, okay, then the relative energies, well, of the molecular orbitals to the atomic orbitals they have been constructed from can be very similar, but generally the interbonding orbital is a little bit further away from the atomic orbitals than the bonding molecular orbitals are. It cannot actually be the opposite case just because of the law of the conservation of energy. So if it was the other way around, basically you would create energy, which cannot be the case because of the law of the conservation energy. However, you can always lose some energy. Okay, therefore, essentially this distance and this distance here, it can be in the most extreme case the same, or that distance can be larger than this distance, but not the other way around. Okay, good questions. Any other questions? All right. That means that we have now fully discussed the two-dimensional band structures by one real example. And well, of course, we could now go from 2 dimensions to 3 dimensions. Okay, so now if you wanted to do that, you would have to work with 3 wave vectors. So then you would have kx, ky, and kz. And again, you could vary kx and ky and kz between 0 and pi over a. Okay, so at point chi, kx would be equal to pi over a, and ky and kz would be equal to 0. At point m, basically kx and ky would be equal to pi over a, and kz is equal to 0. And there would be now the additional point r, in which kx is equal to ky is equal to kz is equal to pi over a. Okay, and you could then again think about, well, for a specific example, what is the bonding situation of your crystal orbit at these different points, and then construct a band diagram accordingly. Okay, so of course, as you go from 2 dimensions to 3 dimensions, your band structure would again become more complicated, as has always become more complicated as we have gone from 1 dimension to 2 dimensions. Okay, therefore I do not discuss here an explicit case of a 3-dimensional band structures, as the principles are the same, but only the level of complexity increases. So with that, I actually wanted to close this chapter about band structures and band theory, and now go to the next chapter, which applies what we have learned just now to understanding electronic conductivity in band structures. So you should now be able to see here this slide about resistivities of real materials. So the resistivities, and we mean here the electronic resistivities of real materials, is, well, an electronic property of such a material, and therefore a bonding theory, like a band theory, should be able to explain such resistivities. Okay, let's look at the few resistivities of a few real materials. So you see here on the left-hand side, there are metals, and here on the right-hand side in red, you see a number of other compounds which are not elemental metals. So let us look at the resistivities of these metals here. And we see that they are all relatively similar. So they are all in the order of a number times 10 to the minus 6 ohms times centimeters. So ohms times centimeters is the unit for the resistivity. And you see that these numbers are all pretty small, okay? Even though, but nonetheless, they are not the same, okay? They can still vary over a few orders of magnitude. So for instance, you see that silver here has the lowest resistivity of 1.6 times 10 to minus 6 ohms times centimeters, actually the metal with the lowest electronic resistivity. And for instance, manganese, which has 185 times 10 to the minus 6 ohms times centimeter of resistivity, okay? So that is about 100 times higher. All right. I briefly also wanted to explain the unit of resistivity, ohms times centimeter. So resistivity is, well, an intensive property of a material. So it's not related to the quantity of the material, so not related to how much calcium, how much titanium or manganese we actually have. Okay, so the resistivity, which is an intrinsic property, is related to the resistance, which is an extrinsic property. Okay, so resistance has the unit of ohms, okay, which is associated with the resistor, okay, which has a specific length and which has a specific diameter. Okay, you see such a resistor here. Okay, you have actually a material, okay, through which an electrical current flows into this direction. Okay, so that makes this dimension here the length of the resistor, but the resistor also has an area, okay, which is in this case defined by the area of this square here. Okay, so now the resistance of a resistor is proportional to the length of the resistor. Okay, so the longer I actually make my wire, the higher the resistance in ohm that I will actually measure. Okay, therefore the resistivity associated with that resistance will therefore be inverse proportional to the length of that resistor. Okay, so now my resistance is further inverse proportional to the area. Okay, so that is actually because as my current flows through the resistor, by having a larger area, the electrons have more path actually to flow around points of resistance. Okay, therefore the resistance is inverse proportional to the area. Okay, so for that reason, resistance is equal to resistivity is equal to the resistance of a resistor times the area over the length of the resistor. Okay, so that's how I can actually determine resistivity. Okay, I can easily measure resistance in ohms with an ohm meter. So if I know the length of my resistor and its area, I can easily calculate the intrinsic materials property of the resistivity. And now you can understand why resistivity as the unit ohms times centimeters, okay, it is resistance times area over L. So we have ohms times meter square over meter is ohms times meter. And of course, I could also use a different dimensionality and say, well, I can also measure resistivity in ohms times centimeters to have more handy units if that suits me well. Okay, so at this point, I would also like to define what conductivity is. Okay, so conductivity is then the inverse of the resistivity. Okay, it has the unit, well, 1 over ohms times meter, and 1 over ohms can also be defined as the unit of Siemens. So Siemens is the unit of conductivity, and then the conductivity has the unit of Siemens over meter. Okay, if you wanted to visualize how you can understand that unit, you can imagine that, well, the conductivity is associated with the path an electron can travel without colliding with an atom. Okay, and the longer this path is, and that is given by this unit here in the denominator meter, the higher the conductivity will be. Okay, so this is why conductivity is Siemens over a length scale. All right. So that was a brief excursion into dimensional analysis, especially with resistivities, with resistances and conductivities. Okay. So, but now let's go back to the resistivities of these red substances. Here you see some of them are elements, however, they are not metals, and some of them are compounds, and you see that these compounds are oxidic compounds. So intuitively would say, well, these substances are not metals. Therefore, we would expect that their resistivities should be significantly higher. Okay, so now let's see if this is always true. And you see that it's true in many cases. However, there are also exceptions. And you see that the resistivities actually vary by many orders of magnitudes. Okay, so for instance, for silicon, we have a resistivity of about 0.1 ohms times centimeters. Okay, so this is of course many orders of magnitudes higher than the resistivity of these metals here. Germanium is about similar, but a little bit smaller. It's 0.05. Okay, now let's look at these oxides here. And you see for these two here, you get a big surprise. Rhenium trioxide has a resistivity of only 36 times 10 to the minus 6 ohms times centimeters. Okay, you see that this is actually lower than, for instance, the resistivity of titanium metal. Yeah, so that is a little bit counterintuitive, because we think, well, in an oxide we have an ionic structure, and in an ionic structure we naturally do not have electronic conductivity much. But you see, that's not always true. Here we have actually very low resistivity or very high conductivity for rhenium trioxide. So magnetite Fe3O4 has an even lower, or well, has actually slightly higher resistivity and a little bit of lower conductivity. It's 52 times 10 to the minus 6, but you see that's the same ballpark region as the resistivity for all these metals here. However, some oxides, okay, like for instance, titanium dioxide, zirconium dioxide, and aluminum oxide have much higher resistivities. For titanium dioxide, it's 9 times 10 to the power of 4. For zirconium, it's 1.1 times 10 to the power of 9. And aluminum oxide is super electrically insulating, is an extremely high resistivity of 1 times 10 to the power of 19. Okay. So you see that all of these compounds are oxides, but their resistivity changes by, well, 19 plus 6 is 25 orders of magnitude. Okay. So you see that the resistivity cannot really have, is not really being determined by chemical composition. Okay, so we cannot say, well, we have an oxide here, therefore resistivity is high. It can actually be extremely low. Okay, so obviously this is not the deciding factor. So what is not, if that is not the deciding factor, then what is? Okay, and band theory actually gives a nice answer to this question. So band theory says that, well, the ionicity, okay, the electronegativity difference between the elements in your material is not really deciding here. Okay, what's really deciding is the band structure and whether you have a half or a partially filled valence band without a band gap, or whether you have a band gap between the valence band and the conduction band. Okay, so now this is illustrated schematically here. Now, here in this case, you see the density of states associated with the band structure plotted versus the energy. And you see that you have here that the Fermi level is cutting the band which has the highest energy. Okay, and whenever this is the case, then electronic conductivity tends to be very high, and we have metallic conductivity. Okay, so now the opposite case is that, well, we have a band gap in between the valence band and the conduction band. Okay, so in this case, we have a semiconductor or an insulator. Okay, there's no fundamental difference between a semiconductor and an insulator. It's just that when that band gap tends to be relatively small, between approximately 4 electron volts, then we call it a semiconductor. And when it's higher than that, we call that compound an insulator. So now you can actually have well, a borderline case in which the valence band and the conduction band touch. Okay, so you do not have a band gap, but the density of states at the Fermi level is exactly 0. Then you have something which is called a semi-metal. So actually a single graphene sheet, for instance, is a semi-metal. Okay, so now how can you qualitatively understand why this band structure like this leads to high electronic conductivity, metallic conductivity, and this situation here leads to low electronic conductivity? This is because when the Fermi level actually cuts the band, then electrons can very easily be excited from a ground state to an excited state. Requires very little energy. So you have many excited electrons that can actually freely move through your band, and therefore electronic conductivity results. Whereas when you have a wide band gap, okay, then it takes a lot of energy in order to excite electrons from your valence band into an excited state in the conduction band. So you have far less many electrons available that can move freely through the conduction band, and therefore your electronic conductivity is small. Okay, and as semi-metal, you have an intermediate case. Okay, so these are qualitative considerations. Now, how can we more quantitatively approach electronic conductivity in extended solids? Okay, so even if we have, let's say, half-filled bands with metallic character, not all metals show the same electronic conductivity. Okay, they can still vary by 1 or 2 orders of magnitudes, as we have seen previously for the examples of silver and manganese. So therefore, can we develop a more quantitative theory that would explain such a phenomenon also? So in our approach to this, we first realize that the conductivity is equal to, well, the carrier concentration, the charge carrier concentration. So the amount of electrons that can move, excited electrons that can move freely through our material, times the elementary charge of an electron, which is just 1.6 CO2 times 10 to the minus 19 coulombs, and times the electron mobility. Okay, so not each excited electron is equally mobile. There are differences between electrons in excited states. So that becomes clear when we analyze how is the electron mobility precisely defined. So the electromobility is defined as the elementary charge times the relaxation time, which is just the time between collisions, okay? So as our electron moves through our electronic conductor, from time to time, it will collide with the lattice and it's getting scattered, and this is what causes resistivity, okay? Therefore, the time between these collisions basically determines how mobile our electron actually is, okay? So the last parameter is what is called the effective mass of the electron. And the effective mass of the electron is related to the slope of the particular band. You see here the quantitative formula for that. So the effective mass is 2 pi over h squared times 1 over the second derivative of the energy of the band over the wave vector k, okay? And of course, that derivative has to do with the slope of the band. So qualitatively spoken, the greater the slope of your band, okay, or in other words, the wider your band, okay, the better this is for the electron mobility, okay, because the effective mass m star becomes smaller, and as m star becomes smaller, the electron mobility becomes larger, okay? Therefore, by looking at the slope of the band, we can make estimates on, well, what is the electron mobility of the charge characters? Charge carriers, not characters. Okay, so actually I just see that our time is over. So maybe this is a good point to stop. I just stop the recording here.